So last time what we did was we started off with this chapter on boundary value problems in solid mechanics. So really this chapter is all about just taking all of the things that we have developed up until now and putting them into one problem, a mathematical problem which turns out to be a partial differential equations. So last time I showed you that given a structure, given boundaries, loadings and everything, the objective really is that we are trying to find displacement field at each and every point in the x, y, z directions for a body like this. That's the problem that we are trying to solve. And we said that these types of problems are in general very hard to solve because, of course, finding an exact solution or an exact function that satisfies all these conditions, in general, it's very difficult to find. For some simple problems, I showed you that there are exact solutions that people have developed over the years. But then what we said was that we were going to focus on this particular three-dimensional problem, even though it says one-dimensional, it's a three-dimensional problem. We are going to focus on this problem where all of the behavior is captured by one single variable, the displacement as a function of x. So think of this bar. Think of this as a rubber bar where we have sort of attached it to the ceiling and it's hanging, and in addition to that, we are maybe applying distributed forces onto that bar and possibly hanging something at the end. So this bar, as we said last time, at each and every cross section, the behavior is going to be purely uniaxial. The stress, the state of stress will be, what's the uniaxial state of stress? 9 components, only one of them is non-zero, right? Let's say 1, 1 or 3, 3, whichever one you want to take. All the other stress components are 0. And for the uniaxial state of stress, the corresponding state of strain is these diagonals, this diagonal tensor, where this would be the elongation in the x direction, which is E3 direction that we are calling. The other two would be contractions, in general contractions if Poisson's ratio is positive. Then, but the key thing here is that the state of stress and the state of strain does vary from cross section to cross section. Okay, why? Because I'm applying a body force, which is distributed force per unit volume, to the bar, so that so the value of the stress, if you will, at different cross sections will be different in general. But despite that, at each cross section, we are saying that the state of stress is uniform. So clearly, this is a three-dimensional problem. There is something happening in the lateral directions also. But all of those things can be completely captured by this one function, displacement of x. So that's the displacement in the E3 direction as a function of x. Okay, and we'll take a look at an example today, which will also be very similar to what you need to do for the homework. But what we said last time was, and why are we doing this? This is a relatively simple problem. Why do we care about this problem? The whole idea here is that first we'll study what are typical exact solutions to this problem. This is a simple enough problem. For most problems, we'll be able to write a function that would be an exact solution to this problem. So we'll know what the exact solution to this problem is. Then we are going to try to solve the same problem in an approximate manner. Even if we know the exact solution, we'll try to apply these approximate numerical methods or computer simulation type of tools that we talked about last time to this problem and see what approximate numerical solution we get. Then we can compare the exact solution to the approximate numerical solution to understand what are the consequences of our assumptions that we make when we are modeling these types of things. What are the consequences of the numerical simulation that people do of these types of things. So for that, what we did last time was found that the state of strain is given by this diagonal tensor. All the off diagonals are 0. This diagonal term gives me elongation, which we said that the strain is defined by u prime, that is just du over dx. Okay, strain in general, you remember, is half of grad u plus grad u transpose. But the diagonal component, this guy, is simply partial of u3 with z3, which is equal to du dx. We substituted all of that in the material model, and we came up with this set of governing equations that are corresponding to the original 3D problem. So we still have an original 3D problem that we are solving. But for this particular example, those 3D complicated equations boil down to a set of ordinary differential equations. These are ordinary differential equations where the only independent variable is x. So as a function of the position along the length of the bar, I should be able to tell you what is the displacement at this point, displacement at this point, and so on. Okay, that's what we are after. So let me highlight this box. That the equations that we are trying to solve are these equations. And as I said last time, if you substitute stress is equal to Young's modulus times strain, strain is equal to du dx, and back into this equation, that is the governing equation, divergence of sigma plus b equal to 0, then what we get is just a reduced set of equations. So ultimately, we'll be trying to solve these equations where the quantity in the bracket, hopefully you are able to see, that is just Young's modulus times strain. So that's stress. Prime means du dx, d sigma dx. So that's divergence of stress plus body force equal to 0. And the other two are boundary conditions. One boundary condition at the right end. And again, I've written it in this form precisely so that you can see that this is nothing but the Cauchy stress traction relationship. Traction at the end L is equal to stress acting on the unit normal. Okay, and on the left end, we have a displacement or a Dirichlet boundary condition. So this statement, either of these boxes, these are boundary value problems, which we have simplified from a complicated set of 15 scalar PDEs down to one ODE and corresponding to boundary conditions. And these are the types of problems that that basically I'm sure you have seen before and you have solved before. But very quickly, I'll also mention that an alternative definition or alternative derivation of the same thing is also obtained by, let's say, describing that one-dimensional bar, body forces, and traction. You look at a small element here in the black configuration. Let's say after deformation, it becomes that black segment takes the shape of this blue segment. So displacement here is u of x. Displacement at the right end is u of x plus delta x. You can immediately define strain as, assuming that the strain at this point is uniform when delta x tends to 0. Again, we get the same definition of strain, that strain is equal to du dx or u prime. And equilibrium, we can see that if we draw the free body diagram of this blue configuration in the deformed shape, the force at the left end is given by stress acting on the normal. Normal is -1. So that gives me traction. Traction acting on the area of cross section gives me the total force on the left end. Similarly, the total force on the right end. And if I do sum of forces equal to 0, divide through by delta x, you'll get to the same equation, d of sigma a, where a is the area of cross section, plus ba equal to 0. If area of cross section is constant, not varying like this, if area of cross section is constant, then you can pull area out, and what you get back is d sigma dx plus b equal to 0. The same equilibrium equation that we had up here. So either you simplify from this complicated set of PDEs down to that, or you go through maybe a more familiar way of deriving stress and strain and equilibrium by free body diagram. You get to the same set of equations. Point is, we are going to try to solve this one-dimensional problem. Maybe I should repeat that. We're going to try to solve this three-dimensional problem in terms of a one-dimensional variable. Okay, so keep in mind we are solving a 3D problem, but the only thing that that's needed is an independent variable displacement as a function of x. That's, if we know that, we can solve all the other things in that 3D problem. Okay, so let me describe this example to you, and I'll let you solve this initially for a minute or so, and then we'll do it together. This problem is similar to a column under self-weight. I have a column. Body forces are given by minus rho g. Let's say there is only one direction, so I'm calling it E3 pointing upwards. In addition to that, I have some load at the top, 10 newtons, let's say. Normal at the top face is plus E3, which is just plus 1. Normal at the left face would be minus 1. And the problem says area of cross-section is constant, let's say just 1. Stress and strain are related through some Young's modulus C. And density of the material is given to you, rho. Boundary condition says that the bottom end is fixed. Displacement at x equal to 0 is 0. That's the Dirichlet boundary condition. And the second boundary condition says that traction at length L is equal to the stress at L, which I don't know yet, acting on the unit normal at that end, which is plus 1. That's given to me as minus 10 because this 10 vector is pointing in the opposite direction to x. So TL is equal to minus 10 at gamma L equal to x. Problem simply says, tell me what is the function for displacement and stress along the length of the bar. Okay. So how do you think you'll go about trying to solve this if I were to give this problem to you? Go ahead, Joe. That's right. So you have the system of equations that we are actually, the only equation that we are trying to solve is this. We just want to solve this equation over the length of a bar. So maybe take a minute, see if you can write an expression for sigma, and then we'll do it together.
This problem is a definite problem, so it has no relationship with the material.
This what problem?
It's a definite. I mean, it's just like without any extra constraints. So its stress is just it has no relationship with the material.
Oh, yes. So you're right, but this displacements will be.
It's yeah, but
Anybody want to get me started on this? How should I proceed in, let's say, trying to find sigma? Going by what Joe said, I am just trying to integrate d sigma dx plus b equal to 0. So if I have to find an expression for sigma, how do I do that? Let's take b to the other side. I have integral d sigma is equal to integral of minus b dx. Right? So I'll just integrate this ODE. Integral, and since I'm writing it in an indefinite integral form, I'll also have to have a constant of integration. Okay. So on the left, I'll have sigma as a function of x. On the right, I'll have integral of minus b which happens to be rho g, minus minus cancel off, and dx. Rho and g both are constant, and I could pull them out of the integral. So well, I'll do that as a step, and then equal plus c, the constant of integration. If I pull that out, integral dx would just be x plus c. So sigma x is equal to rho gx plus c. How do I find c? The constant of integration? On the boundary condition. What boundary condition should I use? Right, the traction at the right or the top end is given to me. So I know that sigma L acting on the unit normal here is equal to TL, and that's given to me as minus 10 newtons. So I'll use that. Since sigma at L is equal to rho GL plus C is given to be minus 10, that implies that C is equal to um, minus 10 minus rho G L. Okay, and that means that sigma x is equal to rho G x minus L minus 10. That immediately gives me an expression um, for the stress as a function of x along the length of the bar. That's the uniaxial stress. Clearly, it is a function of x. You would expect the stress would be compressive, right? When x is 0, this gives me a negative number. This is already a negative number. That would be a big negative number, right? So stress would be compressive at the bottom when x is equal to 0. When x is equal to L, this term cancels off and we have minus 10, which also makes sense that the compressive stress out here would be equal to 10 divided by area of cross section, which we have said is 1. Okay. So that's for the stress. How about displacement? How can I find displacement? This entire bar is in compression, so displacement as a function of x, you would expect displacement to be downwards, right? How do I find that displacement? Divide by C and integrate it. Why is that? That's right. So if you just go back on the previous page, you can see that stress is equal to C times epsilon. Epsilon is U prime, so stress is equal to C times U prime, right? So I'll just use the definition of stress. Stress is equal to C times U prime, implies C times du dx is equal to rho g x minus L minus 10. If I integrate both sides by taking C to the other side, now in this particular problem, we have assumed that C is constant along the length of the bar. That may not be true. You could have C varying along the length of the bar if the bar is made up of different materials or a material that is graded. C could be a function of x, but let's, for now, it's simple enough. I'll take C to the other side, du dx, and actually I'll go ahead and integrate that as well. So integral du is equal to 1 over C rho g x minus L integral and minus 10, keep that as it is, 10 over C actually, and dx. Make sense? Anything else? Anything else? Am I missing something? Or constant of integration, right? We always do that, right? For indefinite integration, we cannot miss the constant of integration. So let me actually, to distinguish that from the first constant, let me call this C2. The first one was C1. So now u integral du is just u as a function of x. I'll integrate that expression. So 1 over c rho g x square over 2 minus 1 over c rho g l x and minus 10 over c x plus c2. That's an expression for the displacement. How do I find C2? The other boundary condition that says u at 0 is equal to 0 implies the first term at x equal to 0 does not contribute, the second term does not contribute, third term does not contribute. Immediately it says C2 is equal to 0. Right? C2 is equal to 0. So that immediately gives me the expression for displacement. Since C2 is 0, we don't have to worry about that part. And that's how you would solve an exact solution to this type of problem, right? Let me ask you this. Instead of this simple body force, if it was a complicated function of body force, how would you go about solving this? Here the body force was constant. Instead of that, if I were to, let's say, apply some magnetic materials of different intensities at that and then pull them down by a magnet, that would be a body force for this. But let's say I give you some function that's not constant here. Would this procedure change of solving for stress or displacement? No. Yeah, on the right hand side you have body force. Whatever function I give you, you try to integrate that, and if it's not too complicated, then you can integrate that by hand. And once you have the stress, you can immediately solve for the displacement just by using the definition of stress. Okay. Question? Yeah.
So what, I think I know, what exactly is the body force again? We have the tandem strike and external force on it. The body force is just another force acting on the member.
Right. So it's a column under self-weight. Body force is like weight. So any object has a volume. Body force is the force per unit volume. If this is, for example, a cuboid, then it has some density. I'll take a portion of that volume multiplied by its density. That would be mass. Mass times gravity. That's the body force acting. That's the most common example of a body force. Body force doesn't just mean that it is weight. You can imagine if this is a charged body, and if I have another charged body here, that charge will either repel or attract this charged body. So that force also is going to be a distributed force per unit volume, whether it's magnetic force or electrostatic force or weight, gravitational force. These are all body forces, forces per unit volume. Okay. Any other questions? Okay. All right. So I'll say only this much about this particular problem, these types of problems. Okay. Our focus is not, again, to try to solve lots and lots of these exact solutions to these types of problems. I'm sure you can do that. Our focus, as I said, will be to try to now develop a methodology for finding approximate numerical solutions to these types of problems, which is where we are going to start by framing the problem in a different manner. Okay. So what we did just now was solve what is also called the strong S, or the strong form of the problem. Okay. This was the governing equation, equilibrium equation. I had the two boundary conditions, left hand fixed, or left hand displacement specified, right hand traction, some body forces. I know how to solve this exactly. But what we're going to try to do now is to express the same problem in a different way and see what kind of solutions do we get by using the common methods of numerical approximation. So to do that, we are going to define the problem in a weak form. This is the strong form. I'm going to try to define the problem in a weak form. Just up ahead, I'll kind of make this clarification that even though this equation that we just solved, I'm calling it a strong form, and I'm also talking about a weak form. There is, it doesn't mean that that weak form solution is actually qualitatively less in some way. That weak form solution is just is also a solution to this same problem, but there are small subtle differences which we'll talk about. So here, before I proceed with that, I'll also comment that on the Dirichlet boundary, where the displacement was specified to be some given value u0, the corresponding traction condition is T at 0 is equal to stress at 0 times the normal at 0. Normal at 0 is pointing in the other direction, correct? The normal at 0 is pointing in this direction, which is -1. So along with that displacement boundary condition, I also have the traction boundary, the Cauchy stress traction relationship. And that was the Cauchy stress traction relationship at the right end. So now we'll try to write the same strong form of the problem in a weak form. To do that, I'm going to have to define what is called a functional. Okay, a functional, you can think of that as a function of functions. Meaning this functional that I'm talking about, G, this will take as input two functions. What two functions? A stress function and another function u bar, and the bar is important here. U, you remember we said u was the displacement function, and we later on see that this u bar can be interpreted as a virtual displacement. Okay, so we are going to define a functional which would be a function of functions given in this manner. So we are going to say u bar is some function of x multiplied with my governing equation sigma prime plus b and integrated over the length of the body 0 to L. Okay, that's the governing equation part. Then I'm going to add to it u bar at 0 times the boundary condition at 0, which was T0 minus sigma 0 acting on -1. So that was the boundary condition at x equal to 0. And along with that, I have another boundary condition at x equal to L. So u bar at L plus TL minus sigma at L acting on the normal at that point, which is +1. And that's that. So this is a functional, meaning you give me two functions. Give me a function for sigma as a function of x. Give me a function u bar as a function of x. I can calculate this integral, and hopefully you are able to see that the result of calculating this integral is going to be a scalar. You see that? So if sigma is a function, body force is a function of x, u bar is a function of x, all of that is some function of x, correct? Integrate that function of x over the length of the bar 0 to L, you get some scalar. This guy is a scalar value at x equal to 0. Traction, sigma 0, all of these are scalars at x equal to 0. These are scalars at x equal to L. So the result of all of that is going to be a scalar. I'm going to highlight this functional because this is going to be extremely important, as you'll see going forward. So keep in mind, this is a functional, which just means that it's a function of functions. Given two functions, I'll return you back a single scalar value, okay, which will be represented by this G. So the idea is, or idea of the weak form is that if I can show that for some choice of the stress function and some choice of T0, the value of T0, which is the reaction at the left end, if for some sigma and some T0, if I can show that this functional, this G functional goes to 0 for all U bar functions in some function space, I'll talk about that also in a little bit, then what that means is that everything that U bar multiplied here, that goes to 0. Everything that U bar at 0 multiplied, that's all this, that goes to 0. And everything that this multiplied goes to 0. Okay, so I've not done anything anything drastic here. All I'm saying is that we had this original strong form of the problem. I'm going to define, using that strong form, I'm going to define this new functional where the equation that I want to solve is embedded in here, multiplied by some arbitrary functions U bar. The boundary condition at the left end multiplied by the arbitrary function's value at x equal to 0, and the boundary condition at L multiplied by the arbitrary function's value at L. This logic is more important to understand. I hope you see that if what the statement says is that this G must go to 0 for all possible U bars. So think of U bars as possible functions that you could pick out of this space of functions. Clearly, you could cook up any function you want for U bar. That's a virtual displacement. Okay, you could cook up whatever function you want. Somebody might choose this blue function, somebody might choose that green, red, whatever, right? There are infinitely many choices of functions there. If it so happens that no matter what, no matter how many functions you choose, if it so happens that this functional, the value of this functional goes to 0 for all choices of U bar, for any arbitrary choice of U bar, then the only way for that to go to 0 would be if this is 0, this is 0, and this is 0. Make sense? Okay. Question, Kajun?
I'm wondering whether the U bar is forced to satisfy the displacement boundary conditions.
No, it's not. I'll talk about that. But okay. So here we are saying that this functional goes to 0 for all possible U bar. The only way that can happen is if the things in the brackets are 0. So I'll write that again. Sigma prime plus b equal to 0. And the boundary condition at x equal to L is, we write that in blue just to be consistent, TL is equal to sigma L acting at +1, and at x equal to 0, T0 is equal to sigma at 0 acting on normal at the left end. So this logic is what is called the weak form of the problem statement. This is W. The strong form of the problem statement was find a displacement as a function of x that satisfies that governing differential equation. The strong form was find stress function, find displacement function such that this governing differential equation is satisfied and the boundary conditions are satisfied. Now the weak form of the problem statement is that find stress function and the underlying displacement, the underlying real displacement function, and find the reaction T0 such that this G functional, this long G functional goes to 0 for all possible U bars. This part of the problem is extremely important. Unless it goes to 0 for all U bars, all possible U bars, we cannot claim that these three bracket quantities are 0. Okay, and this is also called a method of weighted residuals form of the weak form, because essentially you can think of this bracketed term. You can think of this bracketed term as some function of x, which is a residual. You want a residual to go to 0. That's a residual force. So you want the residual force to go to 0. This is the residual at the boundary condition at the left end. This is the residual at the boundary condition at the right end. So you want these residuals to go to 0, and you're taking that residual, multiplying it by some weighting function, and therefore it is called the method of weighted residuals of the weak form. So all I've done is just stated the problem in a slightly different way. It's still the same original exact problem. Okay. Um, Now I'll talk a little bit about why this is the case. Uh, why solving this is the same as solving the original strong form of the problem, and that actually relies on what is called the fundamental theorem of calculus of variations. If you remember from chapter 1, we talked about fundamental theorem of calculus. Remember what that was, fundamental theorem of calculus? Right. So basically, it says that if I have a function f, then the integral of the derivative of that function is just function value at b minus function value at a. That was fundamental theorem of calculus. This is fundamental of theorem of calculus of variations, and there is what this says is that if, and actually I missed out something here. I missed out a very important sign convention. We will take all of that and we will multiply that with a minus sign in the uh, so everything on the right hand side in this big black brackets and put a negative sign in front. Okay, that's a convention, and I'll tell you why that's the convention. But okay, it relies on the fact that if you have some functional of two functions, sigma and u bar, then if you have that functional where we have that residual sigma, in our case that residual is nothing but sigma prime plus b. We have some boundary condition a0, which we are, in our case is t0 minus sigma at 0 acting on -1, and finally a at l, which is tl is equal to sigma at l times +1. Let me make some more room here. If this is 0 for all u bars in that function space, then g is equal to 0, a is equal to 0, and al is equal to 0. And this statement that we wrote here for the weak form, that relies on this theorem called the function calculus of variations. I'm very quickly going to give you the reasons for why this is true. A detailed proof is a math topic, but I'll give you a rough idea of why this works. So we are trying to show that if somebody gives me that g functional, okay, and if that g functional goes to 0 for all possible u bar in a space of functions, then is it possible for the residual to be non-zero, if that's possible at all. Okay, so we are going to prove that in a counter argument. Let's say that there is some function g, something like that. I don't know what that g function is, that residual function. Let's say we have some non-zero g residual function. Okay, now since we know that the g functional has to go to 0 for no matter what choice of u bar we pick from this space, there might be one particular u bar function in there which matches this g function exactly, right? That where g is equal to where u bar is equal to g. So I'll pick that particular u bar from that space of infinitely many functions. I'll pick that function which I don't, which matches this this function exactly. I don't know this function, but I'll do that. And if I take the product, then this is nothing but g square. G square of any function will always be positive, correct? And it would go to 0 here and something like that. That would be what g square would look like, correct? It cannot be negative. Now, g square integral over dx would be just the area under this curve. The area under this curve is essentially g of sigma and u bar. That's the functional. For this to be 0, it has to be true that g is equal to 0. Okay. So we started out with an argument that let's assume there is some non-zero functional, there's some non-zero function g that that this argument that we laid out is satisfied for. In order for that argument to be satisfied, we can pick any function out from this space. So we picked that particular function that matches this exactly. So this became equal to g square. If I pick u bar is equal to g, which will always be positive, integral of that would be the functional that we have. The only way that this functional can be 0 is if g is uniformly 0. And that immediately means that contradicts our initial assumption. So therefore, there is no non-zero residual for which this condition will be satisfied for all possible u bars. And therefore, the residual has to be equal to 0. Therefore, sigma plus b, the equation is satisfied. And finally, you can also, I think maybe I did mention here, for this first part, we are assuming that u bar is 0 at the two ends. And then if you relax that condition, you can also show that since u bar at 0 is arbitrary, therefore this has to be 0. Since u bar at L is arbitrary, therefore this has to be 0. And we get the governing equation is 0, and the two boundary conditions have to be satisfied. Okay. All of this argument does rely on this fact. So coming to your question whether this u bar has to be 0 some places, the only condition that that this fundamental theorem of calculus of variations relies on is the fact that I should be able to calculate this type of an integral. I should be able to integrate this function. Okay. If this function itself is not integrable, then my argument fails. Okay. That's the only restriction on the choice of u bar in this. So the idea is from this infinite space of functions from which you are pulling this virtual displacement u bar functions, the only restriction is that integral of u bar square has to be finite, has to exist. Otherwise, my logic breaks down that I have up there. Okay, and this is called square integrable. That if I have a function, I square it, I try to integrate it. If that integral exists, then u bar is square integrable. And these types of functions belong to a space of functions which is called L2 space. And I'll tell you why that is. L2, where L stands for a person, a mathematician by the name of Lebesgue. This integral is a Lebesgue integral. The integrals that you have been doing till now most commonly are usually Riemann integrals. Lebesgue integrals are a different type of integrals, slightly more general. But the question arises, what kind of functions would those be where u square integral does not exist? If you think of all of these functions I have drawn here, the blue function, this function, black, red, green, whatever, this blue function is actually discontinuous. Can you tell me whether this blue function which is discontinuous, is that square integrable? You could easily go to every point on that line, find the function of the value of the function at that point, square it, it will give you some other value. Keep doing that, goes to 0 here, some 0 here. Wherever there is a discontinuity, that's the point where in general that function is not defined. So except for those 2 points in this case here, the square of the function is well defined. So the integral of the square of that function is also well defined. If you have finite number of discontinuities, that's not a problem. You can still calculate the value of that integral. The There is this one class of functions and some other classes of functions as well, but one common class of functions is called the Dirac delta function. Hopefully you've heard of that before. That is not square integrable, and let's see why that is. The Dirac delta function, hopefully if you remember, is defined in this way, that integral from minus infinity to plus infinity of the Dirac delta function at some point x minus x0, that integral is always equal to 1, which if you were to think of it is kind of a infinite value at x0 and 0 everywhere else. That's a Dirac delta function. And the way I'm showing it, it's a limit of the function that I've drawn in black and blue. So the function in black, if you see, it's centered around x0. So that's x0 minus epsilon and x0 plus epsilon. And the value at x0 is 1 over epsilon. Okay. So you can clearly check half times base times height. So half times 2 epsilon times 1 over epsilon, that integral is equal to 1. As epsilon tends to 0, as I shrink that, the height of that triangle keeps on increasing. So in the limit, when I shrink it down to 0, I get that infinite function represented by that green arrow. That's a Dirac delta function. And you can show that if you were to square it, integrate it, you get 2 over 3 epsilon. And clearly, as epsilon tends to 0, that integral goes to infinity. It does not exist. You cannot find that integral. Therefore, the Dirac delta function is not delta function is not in L2 of 0 to L. Okay, so that's one example of functions that you cannot pick, but most other functions are fine. And looks like I've already exceeded my time here, so I think we'll stop here, and I'll come back on Wednesday next week, and we'll go more into the details of these weak forms. For the quiz, all I would expect you to do is to be able to solve these types of problems. Okay, solve this one-dimensional ODE. That part I will expect you to do. Nothing of the rest of the lecture that we did today. Okay. All right. So I'll see you at 3:30 this afternoon. Otherwise on Monday.